Okay, so we want to look at the load transfer. This is now load being transferred from the matrix or the resin to the fiber itself. So when a fiber reinforced composite is loaded, the matrix acts to transfer the load to the fibers. Because if you think of a composite, let's say that's your component. Of course, the fibers are going to sit inside the composite like this, and then you have to hold it maybe like that with a clamp or whatever, and then you pull it maybe in that direction. So the load transfer agent is the bond between the matrix and the fiber, which is represented by the interfacial shear stress. So interfacial shear stress would be, if this is your fiber, maybe that shear stress, and there's your matrix all around it. So the interfacial shear stress is that along the outer surface of your fiber. The the high shear stresses at the ends of the fiber mean that the metal matrix will flow plastically. And in order to fully utilize the high strength of the fiber, it's necessary that the plastic zone in the matrix not extend from the fiber ends to its mid-length before the strain in the fiber reaches its failure strain. So you don't want it to go into a plastic deformation before it reaches that failure strain. So we need to look then for equilibrium of forces. So how to get this low enough is to actually limit the length of the fiber. So the longer the fiber is, the more it's able to transfer the load from the matrix to the fiber. And so that transfer becomes problematic. Or becomes too high, and then you can break the fiber. And that's how critical length is just short enough so you can't break the fiber with a matrix. So if we neglect strain hardening, then the shear stress on the fiber will not exceed the yield stress. So taking an equilibrium of forces between the actual, so what we're saying here is, of course, if you look stress strain, and there's your yield stress, and we're saying there's no strain hardening, so it stays flat here. So the shear stress will stay at the yield stress. So taking an equilibrium of forces between the actual stress in the fiber and the shear stress acting on the length of L over 2, because the fiber is loaded from both ends, we get the following. So we've got, there's your fiber, half of the fiber, and then the other half, maybe like this. Apply force. So you get that force in the fiber, which is the stress in the fiber times the cross-sectional area of the fiber. So D would be the diameter of the fiber. And then the shear stress, of course, your shear stress acts like that. And that will be all around the circumference of your fiber. So that's the circumference by D times that L over 2. So half its length. Times, of course, the shear stress. And so we get the critical length of the fiber is equal to the breaking force, or the force in the fiber, sigma F, times D divided by 2 tau 0. Tau 0 being the shear stress acting on the fiber. So when the fiber exceeds LC, it's possible to load it to breaking stress by means of load transfer through the matrix, deforming it plastically around the fiber. So you want to make sure that you don't exceed LC. That is your critical fiber length. And remember also that that will be your yield stress, tau 0. Okay, then lastly about fibers and composites, it's very important how we orientate the fiber. So you can understand if the fiber, if you apply a load in this direction, and the fiber is also oriented in that direction, then of course you're going to get your best, highest strength. If it is oriented like this, it's really not going to be strong. It's going to be more of a defect, and that's what we see. So on the X, we've got off-axis angle. So if it's 0, it goes up, it's high. If it goes to 90 degrees, it goes very low. So on this side, it's your composite strength. So very important how you orientate it. So unidirectional array of fibers in a matrix is highly anisotropical material. So we're going to find that it just strength in one direction. But this is compensated in practice by using a cross-ply laminate, so in which the fibers have different orientations in each layer. So maybe at first you have your fibers like this, and then you come and you put down the next layer like that. And so it becomes a cross-fiber laminate. And also maybe if you have a sheet like that, if you roll it into a cylinder, then of course you add even extra strength. And then lastly, something that's very important just to remember is that if you look at a tensile test, stress strain, if you look at influence of temperature, you'll see that increasing temperature causes a drop in the stress, or the UTS, which is quite obvious. As you go to higher temperatures, your material becomes weaker. But what is maybe not as obvious is the effect of strain rate. And so we see that as your strain rate increases, the strength also increases. But in both of these cases, like for temperature, as you go to lower temperatures, your ductility decreases. And the same here with the strain rate. As your strain rate increases,